All right, thanks for being here again today with me. All right, next topic, as it says, is wave interactions. We've been talking the last month or so about sound waves and now light waves. And one of the things in the AKS for this unit in particular is wave interaction. So I'm going to run through the 4 different types pretty quickly today. Again, as we go through, please pause when you need to so that you have more time to write down, hopefully, the notes that you're taking so that you can show them to me and get some extra credit. But also so that you'll have them when you're answering some questions later on. So today is largely just about recognizing 4 vocabulary words and situations in which they happen, and hopefully understand why and when they happen. So the simplest one is our first one, which is reflection. We have a cute little doggy here seeing his reflection. But by definition, this is just simply when the wave hits a barrier and it bounces back. Usually when we're looking at a flat mirror like the dog is right now, the light is hitting the dog, bouncing off the mirror, and then back and forth. It's just going to be a straight reflection. But oftentimes the angles that we're having are not just a straight angle. They will bounce off at an angle. So there's a law of reflection, and it's pretty simple. It's just that the angle with which a wave hits a barrier is going to be the same as it leaves it. And you can see the diagram, the way that this was illustrated is the incident ray, and this is the incoming. If it hits a mirror, it's going to bounce over here and reflect off of it. So that kind of explains why if you aren't looking at a mirror straight on and you're kind of looking at it at an angle, you'd no longer see yourself. Because if your face is over here where the arrow for the reflected ray is, and you're looking at an angle onto the mirror in this direction, what you're going to end up seeing is whatever would happen to be over here. This is why you no longer see yourself. When you're standing right in front of the mirror, you're looking straight in front of you. Obviously, the light's just bouncing right back at you. So as your eyes move further and further to the right on my illustration, you're going to end up seeing whatever is more and more to the left. And again, you've experienced this pretty much every day when you've stepped in front of an angle, or excuse me, in front of a mirror. So one of the things we have on here is a thing referred to as normal. First semester, we had a thing called the normal force, and that was the force that was going perpendicular into the surface. This normal line is kind of similar to that, and it helps us as a kind of as a reference point. So when we talk about the angle of incidence and the angle of reflection, we're going to make that angle with this normal line, which again is being perpendicular or 90 degrees to the mirror. So if this were a 40-degree incident ray, this would be a 40-degree angle of reflection. And we'll use this word normal here in a moment, again, when we do refraction, so it doesn't go away. But again, it helps us to kind of define the midpoint or the 90-degree angle when we're talking about things coming in. With slinkies, we really didn't see this when we used the slinky because we were mostly holding it. But if a slinky in this picture is moving from left to right, if it hits something that's inflexible, which would be like if you and your partner were doing the slinky and your partner was holding the slinky and wasn't letting it move, then typically what we tend to see is that as the wave comes in and hits the object, when it goes backwards, it kind of flips around to the other side. And again, y'all may have seen that when you were using your slinky. If in fact we actually change this to where it's actually can move up and down, for example, instead of holding it rigidly, if you were holding a string and then that string was attached to the slinky so that the string could actually move up and down, we get a slightly different pattern. So it actually bounces back on the same side. Again, we're probably not going to be tested on any of this, but it's just some wave phenomenon that we see that whether or not the slinky wave bounces back on top or bounces back on bottom has to do with whether or not the object that's holding it is able to move one way or the other. So again, probably not a priority to remember this one. The second type of wave interaction is refraction. Definitely do want to mention this one. Again, this is kind of a weird picture from an old Life magazine. And again, it's our eyes somewhat playing tricks with us, but they're not really playing tricks. Our brain is just seeing what the light is telling us to. And so when light goes from one medium to another one, say from water into air, it ends up bending. So let's look at the reasons for this. So one of the main reasons we're talking about this is like with the straw that's sticking out the top, we can see as it enters the water that it looks like it's broken. And again, it's obviously not broken. It's our eyes interpreting what we see. So the refraction has to do with the change of the speed of the light wave. Now, up until this point, we've said the speed of light is 3.0 times 10 to the 8th meters per second. but that's usually in a vacuum, and we don't really have those on Earth, but it's close to the same speed in air. It slows down a little bit in water, and it slows down a little bit more when it goes through a clear solid. And so when you're looking at the top part of the straw, all the light that is hitting the straw and reflecting off the straw is going through the air and coming into your eyes, and it's basically making a straight line. So our eyes see the straw where it actually is. Now, when it's in the water, again, for us to be able to see it, light has to reflect off of the straw. So imagine a light wave leaving the straw and coming into your eyes. It's got to go through the water, and then it's got a bit of curved glass or plastic in this case, and then it's going to go into air. So as it goes from the water into the plastic into the air, it changes its speed, and because there's some angles involved, it actually gets bent a little bit. And so the direction of the light changes a little bit. So then our eye actually thinks the straw is not where it really is, but our eye thinks the straw is where the light is coming from as it leaves the glass and coming into our eye. So again, the concept of refraction simply is the bending of light, and it's going to happen due to changing a medium. So as long as the light's just going through air, you're not going to get any refraction. If it's going through still water, you're not going to get any refraction. So what we need is changing medium, usually from water to air or from air to water. The next slide with this illustration, we're bringing back the normal line again, which is the dashed line that's going down. And what we see is, in this case, like with air and water, if the ray is coming in and hits the water, notice it doesn't continue going straight. It bends and it changes its angle and moves towards the normal line. And the reason in this case it's moving towards the normal line is because it travels faster in air than in water. So when it slows down, it tends to move closer to the perpendicular line. And also, as you change this angle, it would end up changing the amount of refraction as well. There's some trigonometry math involved with that we will get to shortly to see how we end up going over that. Now, also write on here that the opposite true is going from slow to fast. So if the water, if the light's coming from the water into the air, which is how we would see it, because if you're looking at a fish or something in the water, again, to see it, you've got to see the light reflecting off the fish. So it'd be going through the water and into the air. It's going to end up doing the opposite. It would move away from the dashed line. So we could really just, if we reverse the course, if the light was coming up to the air, it would still bend in the same direction. And again, it would be bending away from the normal line that we have there. Okay. Our third wave interaction is called diffraction. So we've got refraction and now we have diffraction. In diffraction, one of the key things we see here is there's got to be some kind of a barrier. So the wave is going to kind of be bumping into something, but it's also going to be able to either go around it or to be able to go through it, even though there is a barrier. So this is kind of an illustration of what would happen is if a wave is coming in from the left-hand side and there's a little slit, and we'll probably have a PhET simulation or some other type of lab with this where we can actually see this. When the wave is coming in and it goes through that barrier, it can continue going through it, but you notice it totally changes the shape that it has. It turns into more of a rounded wave instead of a flat wave that's being able to go through. If you change the size of the slit here, you end up getting a change in the type of wave that ends up going through. If we have different numbers of waves, or excuse me, different numbers of slits, we get different numbers of waves. So we will get into that a little bit later. But again, the main thing we want to see here is that waves will tend to bend around the corners of a barrier as long as it's in the same medium. All right, so we've had reflection, we've had refraction, we've had diffraction, and then the last one's called interference. Interference is usually, when we use that word, it's a couple of things kind of bumping into one another for some reason. In football, there's a penalty for interference is when the defender, or in some cases the offensive player, pushes off or it kind of cheats a little bit, as you want to call it. And so interference is going to happen when there's two different waves that are coming towards one another and they hit one another, basically. Okay. Depending on what's going on with the waves, this interference could be constructive, it could be destructive. This is kind of what happens when you're in the car listening to the radio and then you start hearing static. A lot of times that's because there's a radio station from somewhere else. Oftentimes possibly sending its radio waves, and you're in an area where we're kind of picking up both of them. And so you end up just getting some noise out of this. But in general, constructive, as the word tends to say, is a building thing. So this would be if you have two waves that on the same side of equilibrium make a larger wave. I'll show you an illustration of this in just a second. Destructive is the opposite. That's when you would have a wave kind of on one side of equilibrium and a wave on the other side. And when they hit each other, they effectively cancel each other out. All right, so here, in this picture, we've got two waves coming at each other and they're on opposite sides. So you'll notice they cancel each other out. So that was destructive interference. Now, as they bounce off and they're coming back again, what we're going to see one more time is this should be destructive interference, because for a moment, they kind of totally canceled each other out, right? I thought I had a different, oh, we got another one here. So again, that's constructive, because you notice we've got two waves on the same side. Hopefully you can predict this would be destructive because they cancel each other out for a moment. And then when these bounce off again, because they're on the same side, they're going to make a bigger wave to the bottom. And that's also going to be a constructive interference. So the kind of the easy way to predict it is what would happen if we added them together. So if we add them together like this, they're going to grow and become bigger because they're on the same side. But if they're on opposite sides, notice you've got numbers over here that are positives and negatives. So this is like a positive 0.5 and a negative 0.5, and they're for momentarily going to turn into a 0, but they will keep going and move along with that. Right. So in summary, we had 4 different wave interactions. We had reflection, we had refraction, we had diffraction, and we have interference. And then there's 2 different types of interference. So one of the things that we should be able to do is to, given situations, to be able to use which of those 4 words properly would illustrate the, the situation, and also to be able to make some predictions about what might happen as well. So we'll do some practice with that. We'll have some lab activities, we'll have some sims, and we'll have some questions for us to practice with. Thanks.